So this morning, so far, we've been looking here at reinforcement learning, and this is a picture I'm borrowing from Joel's slides. There's a dynamical system which has some state. Your learning agent might have access to that state. Then based on that, decides to take an action, might also get reward along the way, and then this goes around in a feedback loop. And there's many ways of trying to solve the problem of finding a good policy for the agent. And what we're going to look at in this session is direct policy optimization, where we assume there's some policy pi theta. This could be some kind of neural net. It could be something else too. This policy maps from state or observational inputs through some calculations to then a set of a vector of actions or potentially a distribution over actions. So let's take a look at what this formally means. We now have an optimization problem. We want to maximize expected sum of rewards accumulated over time under policy pi theta, where the policy pi theta is what we optimize over. Typically, the policy pi theta is chosen to be stochastic. The reason that's done is because it smooths out the optimization problem. Because small changes in a stochastic policy will result in a small change in expected return, and now you have a nice optimization problem to work with. Why would you do policy optimization rather than something else? Often the policy can be simpler to learn and to represent than a value function or a Q function. For example, let's say a robot needs to grasp something like a bottle of water. All it needs to do is get close and then close its fingers, and that's it. And that might be a very simple policy. Closing might be very simple to represent. But understanding exactly how much value there's associated with closing your fingers and then exactly how you close them and so forth might be much harder to learn. And so by directly looking at the policy and the policy only, it might be easier to solve this problem. If instead you decide to learn value functions rather than a policy, one issue is that a value function doesn't prescribe actions for you. Once you have a value function, to then act, you still need to do something. For example, you need to do one step look ahead. Say, if I were to take any of my set of actions, what would happen, or what's the distribution over things that could happen, then evaluate the value at the next state as well as reward along the way, and see which action is best. You could say, well, I could directly learn Q values rather than V values. That often works well, and we've seen some examples this morning. Where it gets tricky is if your action space is very large. For example, a continuous action space or just very high-dimensional discrete action spaces. Because then the optimization argmax over all actions of QSA can be very tricky. Not saying it's impossible, it's just not super clear how to make that work yet. Another reason you might want to study policy optimization is because there have been a lot of success stories. So the top line here represents some of the older success stories, nothing deep in what happened there. Joshua.
So why would it be easier to choose an action if you're doing directly policy optimization rather than learning Q? I mean, you also have to pick out of many possible actions.
So let's make this a little concrete. Let's make this concrete. So if it's discrete and you're able to output, if your neural net can output a Q value for each possible action, then there's no issue, because then you can just see which one is the highest. But once you move to high-dimensional, let's say continuous action spaces, you try to represent a Q value for every possible state-action combination. You usually don't, it's not clear how to have an output corresponding to every possible action you might take. And so now effectively, maybe it becomes the input to your neural net. You have to actually propagate all the way back to infer which actions maximize this.
So I was thinking about the high-dimensional discrete space, where it seems that you have the same problem in both cases, whether you learn Q or you learn a policy. Isn't it the case?
Let's see. If you have a high-dimensional discrete case,
or the discrete case in general, you have to.
So there are a few things you can do that might still be a little easier with policy representation. So let's say you have a discrete case and there's a bunch of actions you have to choose at any given time. Maybe you're playing multiple Atari games in parallel. You're multiple players at the same time. You're controlling them all, and they're all discrete actions. So a natural thing to set up, let's see, would be that if you have a policy, you would probably set it up from state to action of the first agent, then from state and action on the first agent to action for the second agent, assuming they can act, you control them all. You can think of them as a joint decision rather than simultaneous play, in which case it doesn't matter. So that'd be one way to set it up for a policy. For a Q function, you could probably set it up. So you'd have to set up your Q function to be decomposed on the output in some way that it's easy to recover which combination of actions does best. And there are some tricks people have played. For example, there's a paper by, I think it's Shane Gu, Sergey Levin, Ilya Sitzkever, and one other author I'm blanking on, Tim Lillicrap, I think, that looks at setting up the Q function so it's very easy to compute the argmax. So by design, the neural net is set up so that it's easy to compute the argmax. And they do it by setting up a quadratic, essentially the neural net outputs a quadratic function in the actions. And since it's a quadratic function in the actions, it's easy to find the bottom. So there are definitely tricks people are playing. It's not super clear how to do it in generality, whereas if you go from state to action as a policy, you can use pretty much any mapping. You're less constrained in terms of how you set it up. Another thing to think about is, I mean, this will come back later as you're debating these things, is that there are things you can do to combine both. You can have multiple networks. So you can imagine that you say, well, it's hard to compute this argmax. You could set up another network that computes the argmax, just like you might have an inference and encoding network. And so you can do the same thing here. And if you look at something like DDPG, the deep deterministic policy gradient, it does something a little bit like that. And in general, actor-critic methods will do something a little bit like that, where there's two networks. And one is the policy network, the other one, the value network. And they work together. So top row here are some success stories in legged locomotion, helicopter flight, another legged locomotion one, and pull in a cup game where you have to swing up a ball on a string and get into a cup. And they were all successfully trained on kind of very small representations, nothing deep there, but policy optimization methods were able to succeed at these tasks where the policy was actually encoded with a relatively small number of parameters. And what's changed recently is that it's becoming possible to run these methods with policy representations with very large numbers of parameters. And some example success stories are at the bottom. For example, in Atari, in Mujoko, various simulated environments of dynamical systems, and also even on real robots. And we'll look at mostly the bottom line in this presentation here. But keep in mind that there have been success stories before, often though constrained to small numbers of parameters that are being optimized. So as Joel showed before, you can categorize RL methods in this way, where there's policy optimization methods and there are dynamic programming methods. And actually, the actor-critic methods bring both of them together, where you have both a value function and a policy, and you train them both at the same time. In my presentation, we're going to focus on the left side of this and ending up at the actor-critic methods at the end. Here are the ideas I want to get across. Derivative-free methods, likelihood ratio policy gradients, natural gradients and trust regions, actor-critic, path derivatives, a different way of computing derivatives than the likelihood ratio, a generalization of that through stochastic computation graphs, guided policy search, and inverse RL. The last two are probably for this afternoon. And you'll see that there will be a lot of detail in the early ones, and we'll dig into the math and really understand what's going on. And for the later ones, due to lack of time, we'll go a little quicker, and there'll be referenced what the ideas are, but we won't dig as deep. So let's start with derivative-free methods. If you want to optimize a policy, simplest thing to do is to say, well, let's say I'm interested in maximizing my utility under some policy pi theta. It's maximizing expected sum of rewards. Well, just see this as a black box. You have a policy, you run it, you see how much reward you get. You could change the parameters, run it again, see how much you get. And just not even look inside what's going on. Don't worry about the fact that this is a reinforcement learning problem. It's just an optimization problem, maximizing utility with respect to parameters theta. So we're going to ignore all other information collected. This cross entropy, the one we're looking at here, is an evolutionary algorithm. It means it keeps track of a distribution over possible solutions, which is represented by pi mu I. So mu indexes into the type of distribution. If it's a Gaussian, mu could just be the mean, or mu could be mean and variance. And I here corresponds to the iteration of our population. And then theta is the space over which the distribution lives. Here's what cross entropy looks like. You iterate. You initialize somehow with some distribution over the parameters. Then you start iterating. You sample population members from your current distribution. So you sample a population member, theta E from a distribution P mu I theta. Then you use that parameter vector to execute a bunch of times. You see how well you do. Collect those pairs, theta and utility. Once you've done that for a few parameter settings theta, you check which ones achieve the highest score. So you say, here are my top 10% of parameters. Those survive, quote unquote. And then you maximize the log probability of those population members. And you maximize this over the choice of your parameters in your distribution mu. This gives this, if it's a Gaussian, we'll shift your Gaussian to where the good samples were. And then you repeat, get new set of samples, and keep going. Nowhere do we look inside the box. Completely black box optimization method. It actually works embarrassingly well. Here's a table from a paper from not too long ago. And essentially what it shows is that, so this is on the game of Tetris, which is a standard RL benchmark. It's a game where you have blocks coming down. You need to place them. If a row is full, it clears, and you can keep letting blocks come down. It's been a benchmark in RL ever since people started doing these things. For example, Tiziklis, Bertsikas often in their book reference this benchmark. And traditionally solved with value function methods, it turns out this cross-entropy thing can outdo these value function methods. Even though it's so simple, it doesn't even look at anything underneath. And actually it took till 2013 when a paper came out, approximate dynamic programming finally performs well in the game of Tetris, where these value function methods could finally compete with cross-entropy. And this took a lot of work, even though cross-entropy is so simple. So it's not just in Tetris that this has been the case. Similarly, in graphics, a lot of the graphics animations rely on a cross-entropy-like method, CMA. And so it's a very powerful method, a surprisingly powerful method. There's a caveat, though. It tends to work best when the number of parameters is relatively small. In the Tetris example, the canonical parameterization of Tetris that was being used, unlike the Atari things we've looked at, is to go from the board to a predefined 20-dimensional feature vector, and then run your algorithm on how you're going to weight those different features in your value function. So you're only finding 20 parameters. And so whether you did value function methods in that literature or cross-entropy, you would always only find 20 parameters. General, for these kind of algorithms, you need the number of samples from your population to be roughly comparable to the number of dimensions in your parameter vector. If you can do that, then this can work pretty well. If you work with a neural net, million parameters, then you need a lot of samples to make this practical. Still, very easy to implement, and it's a great baseline to compare with. You at least have some notion of how well your actual RL algorithm works relative to some basic baseline. So something else you can do, just completely ignoring the inside structure of the problem, is just do finite differences. You could say, I have a function, I want to optimize it, that is expected sum of rewards. Let's look at the parameter vector, perturb it, see what the local derivative is, compute the entire gradient, make an update, and repeat. Some challenges there. If you're doing these rollouts, typically they're stochastic. This can be because of the dynamics, because of your policy being stochastic. Both could be at play. And so it could be that you have a function that looks like this. And when you evaluate the derivative based on 2 samples, you actually get something that's sloped exactly the wrong way. Fixes to this? Well, you could take a lot of samples, and it'll average out. It won't be a problem, but that is often what you want to avoid. You want to learn from a relatively small number of samples, if possible. Another fix you can make at times is to fix the random seed. So as you execute your policy, you execute another policy, different setting of the parameter vector. You keep the random seed the same, and so the randomness will interact with your system the same way. And this will give you more consistent computation of derivatives and so forth. The randomness could be in policy and in dynamics. In the policy, you can control it. When you sample actions, given state, you can totally control how you do that. In the dynamics, it might be harder to control. It can give issues. Let's say you're flying a helicopter. You want it to be a good policy. You try a different policy now. The wind conditions are different. If it's more wind, gustier, it's going to be harder to do well. And you can't just look at the outcome of one run and decide that, oh, the second parameter setting was worse because it did more poorly because it might have been caused by this randomness in the environment. So there's some trickiness here in getting this to work. There are some nice theoretical guarantees, though. If you can fix the random seed, how this makes things more efficient than if you can't fix it. let's take a look at a result that was obtained with this.
If you had a generative model of the wind, then you'd be okay.
Yeah, if you had a generative model of the wind, you would be okay. Please bring me one someday.
I'm working on it.
So what we'll see here is a helicopter controlled by a control policy that was found through direct policy search, running things as a black box. So there is nothing looking inside at when the rewards are accumulated. It's just a bunch of parameters that are being optimized by repeated trial and error and looking at the total reward attained. Using the trick of fixing the random seed, the learning is happening in simulation. And then the test that we see here is on the real helicopter. But the reason the random seed could be fixed is because all the learning was in simulation. So this is helicopter reliably hovering. This is actually a hard problem. So stabilizing a helicopter, think of it as balancing a long broom on the palm of your hand. And then you need to constantly look at that broom to balance it, make sure it doesn't fall over. Same thing here for a helicopter. And then some amazing cinematography here where we rotate the camera by 180 in the middle of this video, exposing that it's actually flying upside down. So underneath the policy here was relatively simple, just 12 parameters. If that's the number of parameters, again, these kind of methods can work pretty well. You don't need necessarily much more than these basic methods. But now let's start digging into higher dimensional policies and see what we can do there. What's this likelihood ratio policy gradient? So some notation. Tau will be a sequence of states and actions. Okay? So state at time 0, action u at time 0, and so forth. We'll work with finite horizon just for simplicity of notation and doing the math, but these things carry over if you do more intricate math to infinite horizons and average rather than total reward. What we try to optimize is expected sum of rewards, which we're going to now, for now, write as sum over possible trajectories, probability of that trajectory under the policy pi theta times reward returned from that trajectory. So initially, we're again going to ignore the fact that there's a sequence of states and actions. We're just going to look at it as distributions over trajectories induced by the policy. Later, we'll break it up into the details of states and actions. OK, so this is what we want to compute. We want to compute the gradient of our utility function with respect to the parameters theta. So gradient with respect to theta of sum of roll trajectories, probability of trajectory, times reward of that trajectory. OK, we can move that gradient inside the summation. And now we can play a trick, which we play because we have some foresight of how this is going to play out. It's very easy to see that this is OK. We multiply and divide by the same thing. But it might not be obvious why we're doing this at this point. Once we do that, we remember that the gradient of a log is the gradient of that thing divided by that thing. And we use that in reverse to look at this, get this expression over here. Now it becomes clear why we play this trick. Because if we look at this, we actually have an expectation again. We see that the gradient can be computed by taking an expectation with respect to the distribution that we're working with, distribution over trajectories. So that's why we did this. And we can then evaluate this based on samples. So we can say we have our current distribution that we get from executing our policy pi theta. We get some samples, and averaged over the samples, evaluate this quantity over here, which gives us this expression over here. It's very interesting. The expectation of this is the exact gradient. But also from just a single sample, actually we can get a quantity that on expectation will be equal to the gradient. It's not going to be very accurate from one sample, but on expectation it will be correct. OK, we can actually derive this a different way too, which is kind of interesting and maybe makes it look a little less like magic. Importance sampling. The idea in importance sampling is that you can evaluate an expectation under distribution theta by actually collecting samples under a different distribution parameterized by theta old. And the way you do it is you have samples under theta old, and then you reweight them by p theta over p theta old. Okay? So the first equation says this is essentially the infinite sample case, that the utility can be evaluated as an expectation under an old theta this way. We can then take the gradient of that expression. We can then bring in the gradient inside the expectation. We can then evaluate this expression at theta old. And then again, gradient of log is gradient of the thing divided by that thing. And so this is what we get. And we get the same expression again, that we have an expectation with respect to some distribution theta old of the grad log probability under that distribution times reward. And so here, the ratio comes in because of importance sampling. What's interesting is that this also allows you to see that you can do more than just computing gradients this way. You can actually evaluate from just a few runs under your policy theta old, you can evaluate what that policy will be like in neighboring parts of the space. Of course, the more theta is different from theta old, the higher the variance on this estimate. So you can't go super far, but at least you have an estimate. What's interesting is that this is valid even if your function R is discontinuous, you have discrete state actions, and so forth. So this is really interesting in that you have no reliance on continuity of your reward function here. We assume that the log probability has derivatives, but we don't assume anything on the objective. Let's look at some intuition behind this equation here. So what's going on? We have a policy, pi theta. We do rollouts under that policy, and then can compute this gradient estimate. If we look at it, it says grad log probability of path I times reward under path I. So this gradient is saying, we're trying to maximize the utility here. It's going to say we're going to increase the probability of paths with a positive R and decrease probability of paths with negative R. Important to keep in mind that it actually never tries to change the paths. So it's never looking at those paths and saying, if you just had budged a little bit this way or that way, you would have been a better path. For that, you need the kind of differentiability that exactly we're not assuming. You need a different kind of derivative that we'll look at later. This doesn't do that. It just looks at each of the paths as they were and puts more probability mass on the good ones, less on the bad ones. In fact, a lot like the cross-entropy method, just using gradients rather than what was formulated there. Now let's break this down into pieces. So the probability of a path is the product of the probabilities of each of the transitions. So we have probability of initial state, which I'm ignoring here, and then there is probability of next state given current state in action times probability of action given state. There's dynamics and policy that participate in this, and then multiplied over all times. Grad log probability, log of a product, sum of the logs, we get this. Then if we look at the two sides, the first one actually does not have any theta in it. So actually it disappears. So it's very interesting that when we compute the grad log probability here, dynamics disappear, completely not present in this equation. And so this is what it plays out as its final equation. And so we can evaluate this grad log probability without having a dynamics model. You should also be worried because you say, well, if you don't use your dynamics model, how informative can your gradient really be? And again, we'll get back to that later. But it's nice that you don't need it. And often that's quite helpful because often you don't have a dynamics model readily available. OK, so here is a summary of what we have so far. We're going, in these likelihood ratio policy gradient methods, we're going to compute a policy gradient estimate by that first equation, the grad log probabilities times reward, where the grad log probabilities of paths break down into just sum of grad log probabilities of action given state at each time. And on expectation, this is correct. On expectation, correct, but very noisy. And so we're going to look at a few tricks to make this less noisy, reduce the variance on this estimate. Of course, you can just get infinitely many samples that will also make it a good estimate, but try to get good estimates with a small number of samples. First idea is going to be baselines. Next one is going to be exploiting temporal structure, and then we'll look at trust regions and step sizing to make this even better. OK, this is our equation again. Turns out, if we want to build some intuition here, we can look at what if the reward is always positive. So reward, no matter what you do, is positive. But of course, for some things you do, the reward is much more positive than for other things. This equation is saying you want to increase the probability of everything you've experienced so far, even the not so great things that had relatively low reward but still positive, more so for the things that were very positive, but still, it's a very weird thing that whatever you did recently, you want to increase the probability of what you did. And so essentially you get a lot of fighting, because the not so great things will increase their probability, and then you'll need a lot of really great things to later be experienced to kind of outdo that you increase those probabilities, and it'll be a lot of back and forth before you get anywhere. Okay, so we could consider introducing a baseline. What you do there is you subtract out from the reward some baseline b. What this is saying is that maybe you have some estimate of what is the average that you might achieve. And then what this becomes is increase the probability of things that are better than average, decrease the probability of things that are worse than average. Should always do it. I mean, without a baseline, really this thing will never work. Once you introduce a baseline, at least you have that aspect in place. So this is still an unbiased estimate. It turns out if you do the math, the expected value of this thing is still equal to the actual gradient, but it'll reduce the variance if you choose a good baseline. What's a good choice for B? A very simple thing would be just on average, how much have you gotten from your past rollouts? A slightly more sophisticated thing would be to use a value function estimate that is estimated in a more clever way than just averaging rollouts. OK, now let's break it down more and look at the structure. We have the first equation shows us what we had. We broke it down into steps. We introduced our baseline. Now look at this last part here. That's the sum of all rewards experienced. And this is multiplied in with the grad log probability of actions, no matter where they are along the trajectory. But it's clear that an action at some time t only influences the reward that comes after time t. So it's not meaningful to incorporate rewards from before time t into your grad log probability of ut given st. And so we can do that. You can also do formal math for this. And what you get is then this expression here, where what's changed is that we just sum over future times, not over the past times when we multiply with grad log probability of action given state at time t. This will also reduce variance quite a bit. OK, so that's the basic likelihood ratio policy gradient calculation. Then, of course, once you have a gradient, you need to do something with it. You need to take a step, improve your policy, hopefully, thanks to that step, and then repeat. So the reason you need step sizing or something like that is because it's just a first-order approximation, not even a good one for that matter. Even if it was a perfect first-order approximation, you still needed step sizing, and this is even worse. And so you need to be careful that you don't go too far. In supervised learning, you actually step too far. It's not too bad, because then the next update will correct for it. And reinforcement learning is actually quite different. And earlier there were some questions about the destabilization and so forth on some of these learning curves. And that's exactly the issue here. Reinforcement learning, you step too far, you get a terrible policy. Consequence is that the next mini batch you use, or the next set of samples you use, is collected under this terrible policy, which is an issue, because now you don't get any signal anymore. And best you can do is actually just go back to what you had before, which effectively means shrinking your step size. There's no automatic correction mechanism like you have in supervised learning, where the data is anyway there and will correct you in the future. Here, there's this destabilization effect. Once you get to a bad policy, the signal will disappear, and that's a problem. So simple step sizing would be, I have a great interaction. I'm going to decide how far I step in that direction. It's simple. That's nice. But it's expensive, because you need to, along that line, evaluate how good your step is. So you might have to do rollouts. They might be stochastic, so you might have to do many rollouts to understand how good that step is, and that's not great. It also ignores that you might be able to get more information from the rollouts you already did. That is, maybe you can get more than just first-order approximations out of it, and once you have a high-order approximation, that can tell you where your first-order approximation is valid and help you restrict your step. So let's look at something called trust regions. The idea here is that a trust region characterizes where your approximation is good. Once you have that, you can then, within the trust region, look for the best point according to maybe your first-order approximation, but within the trust region, what the best spot is to be. It's a bit like a Newton method. Newton's method can be seen as a trust region where you have the Hessian as telling you where you can rely your first-order approximation, and you need to stay within some bound around your current point, which is defined by a metric given by your Hessian, but it doesn't need to be Hessian. There are other metrics you can use too. For reinforcement learning, it makes sense to look at this metric here. So this metric here is saying, So this is the first order approximation. We're looking at a change delta theta. First order approximation, of course, would just say go to infinity in the direction of the gradient. That's not what we want to do. This is saying we're going to look within a region of small KL divergence from what we had before. So it's a current parameter theta. We're considering a change to a new parameter vector theta plus delta theta. And we want that the distribution over trajectories after the change is close to the distribution over trajectories before the change. If we can ensure that, then a few things are great about that. One, the first order approximation is probably pretty good if that epsilon is small enough. The other thing is that this whole effect of changes in your policy resulting in a completely different set of states being visited, and now what you learned not being valid anymore, is explicitly being avoided here because it's saying you need to keep visiting the same states roughly on average. So our problem is the following. We want to now solve this optimization problem at the top. Let's look at the details. KL divergence. How do we compute that? Let's break down probability of trajectory into the components. Then let's write out the KL using that equation there. So probability of trajectory is product of probabilities of action given state and state given previous state and action. Fill that in here. Something magical happens again. If you look at this equation, the dynamics here cancels out again. And we have an expression that only involves the policy behind the log. In front of it, there is still dynamics, but the thing in front, that's an expectation, and we can evaluate that based on samples. And so what we get is the following expression here that we can evaluate from samples. We average over the states and actions that we visited. This thing over here, which is the conditional KL between the distribution for the policy we had before and the one that we have after. Question there?
I was just wondering, KL divergence isn't a symmetric measure, right? So if you're defining basically a ball of delta distance away from your current parameters, that why are you using an asymmetric function?
OK, so it's a good question. A natural thing would maybe to say, let's use.
Can you repeat the question?
What? Oh, why do we use the KL divergence given that it's an asymmetric way of measuring distance? And maybe that's not great to measure it in that asymmetric way. One way to symmetrize it would be to say we're going to sum the KL divergences that work in both directions and then work with that. And that could be an interesting thing to do. What's interesting about using it this way is the way the math works out. As you see, the way the math works out is that you can evaluate this based on samples and only need access to your policy. You don't need access to your dynamics short of the samples you collected. If you were to evaluate this the other way, you'd have to also collect data under your theta plus delta theta, but you're optimizing your delta theta, so you'd have to recollect samples every time you're considering a different choice of delta theta. And so this direction is the one that's cheap to evaluate. It has downsides to it in that essentially it makes it only locally valid. The asymmetry will hurt you if you go further away. It does turn out that the second order approximation of this thing is symmetric, and we'll work with the second order approximation of this. And so in that sense, we actually do have a symmetric measure that we use in practice, but as expressed here, it's asymmetric indeed. The way the KL, the way it'll ultimately, I mean, this is future work. I don't know if anybody who's actually analyzed this in enough detail, but the way it'll hurt you that you're asymmetric is that if you were to set it up the other way around, the states you visit under your new policy will play a role in how you evaluate this. And here, only the states you visit under your current policy play a role. And so you lose a little bit there. It's not clear how much you lose, but you definitely lose something. Joshua?
Isn't that an instance of natural gradient?
It will be on the next slide, yes. Once we make it a second order approximation rather than the full expression.
I think it is already natural gradient.
So the question is it already a natural gradient? It will be, yeah. I mean, yes. Could you say what the question is?
You were supposed to say.
I was just saying that.
Oh, an observation.
Very much symmetrically for geometric reasons.
OK, so the observation is that locally it behaves extremely symmetrically. Only when you go further away, it becomes asymmetric. Thank you. Yeah. Yes?
There is an analog to what we do when we train neural networks with gradient clipping. So here, like effectively, your KL is telling you move your parameters in within this ball, and you do gradient clipping, which also says you are not allowed to move outside this ball. Except when you do gradient clipping, it's this heuristic based on the norm instead of the KL distance. I don't know if you have any intuitions of how. I mean,
Yeah, that's an interesting. That's interesting. The point here is that gradient clipping seems quite related to this in terms of limiting how much you're able to update things based on the current data you got. And I think you're absolutely right. And in fact, within RL, there's a recent result from Raymond Munoz and collaborators that looks at a similar idea when you look at importance sampling and you use importance reweighting in these calculations. That he shows that if you clip the importance reweighting at 1 and you can never go above 1, that you can get certain guarantees that at least nobody's able to prove otherwise yet. So I think there are very close connections, absolutely. So here's the problem we ended up with. We wanted the KL to be small. We saw that it can be an empirical KL on conditional of action given state for states and actions that we visited. If we take the second order approximation, it'll look like this, with the thing in the middle being the Fisher matrix. And this is easily evaluated from the gradients we are already computing. And so this is essentially the natural gradient setup, more or less. So this is what we have. Practice, we have first order approximation for the objective, then second order approximation to KL, which can be computed from what we already compute for the gradient. If the constraint is moved to the objective, you recover the natural policy gradient methods that people have proposed several years ago: Sham Kekade, Drew Bagnall, and Jeff Schneider, Jan Pieters, and Stefan Schall. It turns out that it's actually more beneficial to keep it as a constraint in practice. And this has to do with the way, if you change your policy, the samples you collect in the future will drastically change potentially, and you can have a destabilizing effect. By putting a constraint there, it's easier to tune that. It's not much more expensive to have a constraint rather than putting it in the objective. By having a constraint, all you need to do is a Lagrange multiplier in front of this thing to put it into the objective, and then you have one Lagrange multiplier in which you do a dual gradient descent to tune it to get your constraint satisfied, approximately satisfied. It doesn't need to be perfectly satisfied, but close enough to get the right kind of step size.
And this is an empirical?
So the fact that the constraint works better is an empirical finding, yes. The theoretical finding is actually that if you have it in the objective, you can prove certain relationships between that new objective and the actual objective, and you can prove a majorization, minorization type setup where it actually suggests that you want to have it in the objective because now you have an EM-like algorithm structure, that you have a lower bound that you're optimizing. But in practice, it's a lot easier to get it to work with a constraint than with putting it in the objective.
So I don't understand how it makes sense to talk about a constraint when you only have a stochastic estimator of the constraint. How do you actually, constrain when you just have some random variable?
So we want the expectation to be smaller than epsilon of this random variable. Yes. And that random variable, the randomness is f theta, which is we estimate from samples, and delta theta will be the variables we get to change. So the question here is, how do we deal with this, the fact that this is random? In practice, I should probably have said this explicitly. In practice, f theta is computed, but also there's a holdout set, and you can also keep track on the holdout set, how you're doing on that constraint. Even though you're directly optimizing on training data, you can check on the holdout data that you're actually doing well, and then likely doing well on the test data. In fact, for a lot of these things, maybe it's not always totally obvious, but in RL, in a lot of the updates that you do, let's say you now evaluate this optimization problem. Same is true for once you take a step, you kind of want a holdout set to evaluate how good that step actually was to help you validate that you're doing well, rather than just using the rollouts in one batch as training data to fuel this optimization.
That's expensive. For each parameter update, you have to check the value on this holdout set. Isn't that very expensive?
You're already testing it on the trainings on the training data you collected. So you might do, let's say, 500 or 1,000 rollouts, and you keep a few of them out and don't use them. And then can check on those few that you held out to efficiently check if you're indeed doing well.
But you only do it once in a while, not every parameter update.
You can do it every parameter update. Essentially, it would just shrink your step size. If it seems on the holdout data you're doing quite poorly, it would shrink your step size further. Question?
Can you highlight some of the differences between this and relative entropy policy?
So relative entropy policy search tries to constrain the distribution over trajectories, which is a little less clear how to do that exactly. And a lot of the work with REPS is then constraining it to looking at linear dynamical systems or constraint settings to make that work out. And it's really nice if you can explicitly look at full trajectories rather than what we did here. In this case, if your step sizes are small enough, it kind of works out fine because the dynamics cancels. In reps, I believe, but don't quote me on this, that essentially you don't rely on the dynamics canceling, but you rely on other certain properties of the dynamics to still make it practical to compute this. And so when it's applicable, that's nice.
I don't really get why it's different to put it in the cost function as to keep it as a constraint. Shouldn't you get the same answer, which is like the inverted Fisher times the gradient or something like that?
So the question is, what's different about having it as a cost function versus a constraint? Yeah. It's a great question. So the difference is the following. If you put it in the cost function, you would have G transpose delta theta plus lambda, the Lagrange multiplier, times delta theta transpose F theta delta theta. And your choice of lambda will determine what you end up with.
Isn't that determined by epsilon?
Yes. And so if you think of determining lambda cleverly based on epsilon, that's what dual gradient descent does. It'll put it in the objective, have a lambda there, and tune that lambda to match a certain epsilon.
Oh, I see. So it's not just keeping it as a constraint, it's also optimizing for epsilon there.
No, epsilon is fixed. There's a relationship between epsilon and lambda. The Lagrange multiplier and epsilon have a one-to-one relation. But it's not easy to know what that relation is. And so you can either pick your lambda, that's a number, or you can pick your epsilon, that's a number. It turns out in practice a lot easier to pick epsilon and pick a number for that that's stable throughout your entire optimization as a good epsilon to use than to pick a good lambda to use throughout your entire optimization. And dual gradient descent, what it will do is it'll compute the lambda that matches the epsilon of your choice. So it'll do what you want to do, except that the lambda will be automatically tuned to whatever epsilon you chose.
But I don't understand. Isn't this equivalent to having this quadratic term up there with an epsilon?
Maybe we should take this one offline, but I'm happy to talk more about it. Yes?
So if you do this dual gradient descent, you would have like one dual variable for every constraint.
No, well, there's only one constraint. So the question is how many constraints? This counts as one constraint.
Okay.
So one dual variable.
What would be the interpretation of that dual variable?
Say it again?
What would be the interpretation of that?
What would the interpretation be of the dual variable? Not sure. It's how much you need to penalize for KL divergence to ensure that it stays smaller than epsilon. Yes?
So I have two questions for this optimization. First is that
Can you speak louder?
you approximate the KL divergence with the second approximation, unless it's the upper bound for the KL divergence, we can use it. But in your notation, I saw that estimates the upper bound. So if this second approximation is not an upper bound, we might violate the constraint without knowing that.
Okay, so the question is, are we really enforcing the KL constraint if we're looking at the second order approximation? And the answer is no, because it's just an approximation. So we're not guaranteed to enforce that constraint. However, if epsilon is relatively small, then the second order approximation will be quite good, and so it'll be close to enforced. One thing to keep in mind is that we actually don't really need a very particular epsilon constraint. I mean, essentially what's going on here is we're trying to ensure that we don't step too far and that we understand where we can trust our gradient. And that epsilon is a tweaking parameter, right? That's a parameter that you set to get this to work well. And so if we're not perfectly satisfying for some particular epsilon, well, maybe then it turns out when we tweak that parameter, even though with the real KL, epsilon should be 0.012, with this approximate KL, our tweaking result will say 0.01 or something instead. And so, well, empirically it's found that tweaking this epsilon is actually quite easy to do with this particular approximation, and it works quite well. But it's not the case that there's a guarantee on the KL just because the second order is enforced. Let's see. Are we done, or can we do more? Let's see. Deep RL, theta will be high dimensional, and building and inverting that Fisher matrix will actually be impractical because you might have 100,000, a million parameters in a neural net. So it turns out that there's a trick you can play with conjugate gradient to approximate that. Details in the paper, but that doesn't make it practical to do this on high dimensional policies. Can we do even better? Turns out we can do even better. So we just have a first order approximation of the objective there. It turns out with the calculation done to get that first order approximation, you can instead define a surrogate loss function, which is inspired by the importance sampling equations, which is a better approximation than the first order approximation. And for the same cost, you can use that and then do a better local search against that surrogate loss. Thing with the surrogate loss, because it's nonlinear, you'd have to recompute gradients on it and so forth, which might be annoying and time consuming. In practice, what we do is we use the surrogate loss as the objective, but we to evaluate rather than evaluate the gradient. So we compute a gradient direction, search along the direction of that. Well, based on the Fisher and NG, we get a direction. We find, once we have the right lambda, we know what that direction is. Along that direction, then we line search based on the surrogate loss rather than the first order loss. Here are some results that you can obtain this way. So what you see here is a simulator called Mujoko. Mujoko is built by Emo Todorov at the University of Washington. What we see here is policies learned after the learning has finished. So these are different dynamical systems running this likelihood policy gradient with a surrogate loss, with a trust region for the policy updates, and it's able to learn a wide range of policies, different policies for different characters. Here we see the learning in action. Initially, it'll just fall over because it doesn't know what to do. It's optimizing how far forward it gets. The further forward, the better. It's also, in the reward, there's also impact with the ground. Less impact is better. And there's also a penalty for how much torque you apply to each of the joints. There's nothing in there that says what walking looks like, what kind of motion it should generate. So it's a pretty non-informative reward about the behavior that you're supposed to get out. Nevertheless, it's able to actually learn that quite well. If we look at some learning curves, doing this the way I described actually helps. The more difficult the problem, so card pull is relatively easy. A lot of approaches will work well. Once it gets more difficult, like swimmer, it stands out more as a better approach. We're comparing with other policy optimization methods. Hopper is even more difficult, walker is even more difficult, and the difference becomes more and more pronounced in terms of performance here. What's interesting is that this, for example, this epsilon for KL divergence, we can set it to 0.01 across all problems that we run. And so we don't even need to tweak it on a particular problem. It's a very general hyperparameter that works across a wide range of problems, which is nice because often the way you have to go about these things is do a lot of hyperparameter tuning before finally something works. You get a new problem, you have to redo it, and so forth. And this way of formulating this avoids that. That actually also works for the Atari games. Obviously, the Atari games, the initial results were all done with DQN. But this policy optimization works for Atari too, where it's instead of continuous actions, as we had for the simulated robots, here we have discrete actions. Works just fine. And in fact, I'll get back to this later, maybe this afternoon, but the best DeepMind results on Atari are also actually with a policy gradient method right now, not with DQN anymore. Something called A3C. OK, so we've seen policy gradient methods. Now let's start looking at how we can bring in value function estimation to make this better. So this was our likelihood ratio policy gradient estimator. From samples, we can evaluate this. And keep in mind, what's in there is sum of rewards, future rewards after the current time, minus value of the current state. I mean, it doesn't have to be value. It can be any baseline, but value tends to be a really good choice, because then you compare what you achieved with respect to what you achieve on average under your current policy. So you would increase probability of good actions, decrease of bad actions. Now, if we look at this quantity over here, sum of future rewards, what is that? You've seen this quantity this morning. It's essentially your Q value of your current policy from that state, taking that current action. So it's a sample-based evaluation, single sample evaluation of the Q value. So it's going to be very approximate. There's no reason we should use that single sample estimate. Probably better to replace it with some other estimate that doesn't suffer from the high variance you get from having just a single sample. It also will have no generalization from rollout to rollout. If you have some kind of function approximator, that can help. So what we'll do is we'll reduce variance on this by introducing discounting and by introducing function approximation. So this is interesting. Often when people use discounting, they consider it part of the definition of the MDP. We're not going to do that here. So we're interested in maximizing expected sum of rewards over horizon H, but we're going to think of discounting as a tweaking parameter that will help us reduce variance on things we estimate for the thing we really try to solve. So original Q estimate from one sample would look like the top line. An alternative estimate looks like this. It's not on expectation going to be correct, or because we're discounting future things, and that's in reality not what we care about. But what happens is that the longer this rollout is, the higher variance. And by discounting, we counter this a little bit so that we don't have increasing variance as much with the length of the rollout. So this is just a variance reduction trick here. It's not changing the problem definition. We still want to solve the original problem, just reducing variance. Actually makes a big difference. Another thing that we can look at is if we look at this, the first line is what we looked at so far. The second line is another way of writing this. Expected sum of rewards is the same as expected reward at the first time plus gamma times value, which is expected sum of rewards, then onwards. Or we can write it this way. Or we can write it this way, and so forth. There's many ways of writing this expectation. If we happen to have a way of estimating a value function, we can use any one of those. Okay? So in generalized advantage estimation, what you use is an exponentially weighted average of those. And this, of course, dates back to TD lambda and eligibility traces, where this is also being used for value function learning. But so this is the idea here, is that we can combine these. Why would you want to do this? It seems like if you had a good value function, clearly the one R0 plus gamma times the value would be the one that you want to use. But the truth is, in practice, you don't typically have an amazing value function. You have a reasonable value function, but not amazing. And because you introduce just a reasonable value function, what will happen is this estimate will become biased. It's not unbiased anymore. That value function introduces bias. And so, yes, we want to use it to reduce variance, but we also want to make sure that we stay somewhat close to the unbiased estimate, and hence the trade-off between the two. And then the trade-off can be done in a very gradual way. It doesn't have to be just the first two lines being averaged, but you can average all possible lengths of rollouts capped off with value function. Here's an example experiment. What you look at here is lambda on the horizontal axis, gamma on the vertical axis. Remember, the thing being optimized doesn't have a gamma. The gamma is just used as a variance reduction. What you see here is, as a function of lambda and gamma, how well this policy gradient method will do. And we see that there's clearly a best there in the middle, where gamma is about 0.98 and lambda is 0.92 through 0.98. That's the range where this works best. So actually, it's interesting to go back and see what that means. So a large lambda works pretty well, which actually suggests that large lambda means you're willing to look pretty far, actually. And so it's actually in this particular problem, it prefers the sum of rewards over it bringing in too much of the value function estimate. Of course, it's going to depend a lot on how many rollouts you do. The more rollouts you have, the better that sum of rewards will be. The less rollouts you have, the more you'll want to depend on the value function that lambda will shift.
Doesn't it depend also of where you are in training? Like if V is better at the end?
So that's a good question. Would it also depend on where you are in training? I think it would. I haven't seen such experiment, but I imagine that as V gets better, if you had any kind of estimate of how good your V is, you would be willing to trust it more. At the same time, once you're already doing very well, your updates will be small, and maybe you actually don't want to use V because you want your fully unbiased estimate to get the final little bit. I'm not sure how it would play out.
It definitely results on the gamma aspect.
Okay.
Your gamma tending towards that. There's a nice paper by Rena's student that shows that for gamma.
That gamma becoming bigger over time is better?
Gamma tending to the true value of gamma, the test value of gamma, as you accumulate more data. And he has some theoretical analysis, theoretical characterization also.
Is this a recent paper?
This is by Manlin.
Yeah, so there's an interesting paper in Satinder Singh's group that looks at model-based RL largely, but essentially what they look at there, they look at also what you can do by changing gamma and why you might want to change gamma. And the idea there is the following. Let's say you do model-based RL, you have an approximate model, you then plan in that approximate model. You won't get the perfect plan because the model is only approximate. And because of compounding error over time under your dynamics model, the further in the future you look, the less accurate you're planning against those futures. And so discounting could ensure that you don't come up with some totally amazing plan, seemingly that the very last step gets you this gigantic reward, but actually the model only allows you to do that, but the real world doesn't let you get there. And have a really nice analysis. I think what's really intriguing there is they have a theorem that says we can measure if you're given an MDP, we can measure how many, so as a function, so if you're given an MDP, and let's say you were allowed to change the reward function in the MDP. As you change the reward function, you'll get different optimal policies. And then the larger your discount factor, so even an MDP, but you can change the reward function. A change in reward function might result in a new optimal policy or not. The longer your horizon, the more optimal policies exist as you vary your reward function. And so the longer your horizon, the more likely you can overfit to something because the space of policies you're going to be choosing from is larger because there is more policy that could potentially be optimal on this longer horizon. And so that's a really nice theoretical guarantee. Thanks for pointing it out, Joel. Here is what happens in 3D. So without this generalized advantage estimation, actually the precision policy optimization doesn't work in 3D or not within the amount of time corresponding to our patience of running experiments. But with all of this machinery, this actually works quite well. Initially, of course, it falls over because it's a random policy, but over time, it gets better and better and better. Again, the reward function is very simple. Further north, the better, less impact with the ground, better, and some penalty for amount of torque at each of the joints. Nothing in there about what motion looks like, which is often done to generate simulated motions, use a motion capture system, and then try to match that. That's not what's done here. You can use the exact same thing for a different robot. This is again in the Majoko simulator built by Emil Todorov at University of Washington. And without any change, just a different robot put in front of it, it's able to learn how to get as far forward as possible. Actually, something quite interesting that happens here is that it finds a gate that is totally unrealistic for the real world, but is very, very fast in the simulator. So RL could be used as a way of debugging simulators. Here the reward is whether the head is at standing height or not, and measuring distance from standing height. just going to contrast this for fun with what happened at the DARPA Robotics Challenge just a year ago. I'm by no means claiming this is the best thing you could have seen if you were there, but it's definitely some of the things you would have seen if you were there. Suggesting that this is a hard problem to get to work, even if there are some solutions out there that work at some situations. I want to now tie this into A3C, the Async Advantage Actor Critic. So not too long ago, there was a paper led by Vladimir Nee at DeepMind looking at asynchronous deep reinforcement learning, where he wants to run it on as many machines as possible to see if that can speed things up. The paper had Q-learning in it, distributed Q-learning, as well as policy gradient. That's what I'm going to discuss here, because if you look at the learning curves, the yellow is the policy gradient method. The other curves are the Q-learning methods. You can see that actually the policy gradient method ends up doing better than the other methods. What they used is the generalized advantage estimation. So a value function is being estimated. That in turn is being used to estimate a Q function. And then the Q minus V gives you the advantage, what's multiplied with your grad log probability. That's, of course, run over multiple machines here to scale it up. They don't use the trust region part. The trust region part is second order, so it's a little trickier to run that on multiple machines and get it to work. I'm not saying it's impossible, but that's probably one of the reasons people haven't used the trust region over multiple machines at this point. It's a good challenge to try out. So what you see here is that it actually works really well on a wide range of Atari games too. OK, I have till 12:30, is that right? OK, so we have 20 minutes left to do the second half of our bullet points. That's actually not entirely true, because we also have half an hour this afternoon, and also these are a lot shorter, actually.
It's good to leave a few minutes at the end for more questions.
OK, then I'll leave the last two bullet points for the afternoon and just do these two. Path derivatives. We've been looking at gradient-based policy optimization. Let's look at what this actually looks like in a graph. You have state at time 0, state at time 1. State at time 1 is a function of state at time 0 through, and also of the action through some function f, which is the dynamics model, which in general is going to be stochastic. Then there's a reward as a function of state. It can also depend on action, but for simplicity, let's assume it just depends on state here. And your state affects the action you take. Computation graph corresponding to the problem we've been solving. If you look at it this way, kind of say, well, why are we computing gradients in this kind of funny likelihood ratio way? We know when we have graphs like this, you can just backpropagate through it, get gradients that way. Computing gradients that way, that's the path derivative method of computing gradients. It's a different way of computing gradients. Let's look at that now. So, can we do this? Let's say we had a current rollout, which tells us the quantities at each of these nodes. That's the forward pass in this network. Can we follow it up by a backprop pass? Well, why not? Let's see. Derivative of u with respect to theta I, each of the entries in theta, is sum of derivative with respect of each of the terms r with respect to r depends on s, then s depends on theta. So we have a chain rule there. We need then s with respect to theta, which s depends on theta through the previous state and the dynamics, as well as through the action and the dynamics. Again, just a chain rule. And then the action depends on theta through the policy. So this is just chain rule, nothing special there. You can do this. You can do a backward pass, compute this. This assumes that you can actually evaluate all these quantities. So let's assume for now f is known. The dynamics is known. F is deterministic. Then we can definitely do this. And we can just backprop and optimize our policy that way. It'll use the dynamics model, which is probably a good thing if we have it. And it'll probably give you more accurate gradients than the likelihood ratio method. It does depend a little bit on these derivatives existing. So there are more assumptions here. The difference is we assume r is differentiable, which we didn't assume before. Before you could have an r reward that's only good when you're at the goal and then drops to 0 everywhere else, things like that. That's not going to work here. It assumes f is known. It assumes f is deterministic. As we progress here, r will remain differentiable. I'm not going to be able to get rid of that. Maybe somebody can, but I'm not able to in these slides at least. But we'll see if we can relax these assumptions here. So first one, f is known. You're collecting data. You could use the data to build a model. You could do supervised learning from ST and UT to ST+1. That's f. So you could, in principle, in addition to doing this policy optimizations, train a model, plug it in here, do this. This definitely have to worry about the accuracy of your model and compounding errors, and you need to think about that. But f being known is not a super strong assumption necessarily. There's fixes to that. How about f being deterministic? Let's look at a simple place where it's quite intuitive how to fix this. Let's say s at time t+1 is a function of st and ut plus some noise wt. Okay? Then if we have a simple sample trajectory, we can actually back solve for the values of w. We do the rollout. We can see what our states and actions were. Assuming we know f, we can see what the difference is between st+1 and f of st and ut. That's wt. We actually know that. Once we know wt, we actually know the dynamics. Everything is known now. It's actually not stochastic. It's slightly overfitting to the rollout you just did, but that's what it is. It's just one sample trajectory. And you can apply the exact same thing again. Okay? So that's nice. Even for f stochastic, especially in the simple structure, you can reapply the same idea. Of course, with a single rollout, be careful because you will be overfitting to the sequence of noise that you experience. You need more than one rollout to do this well, but it's possible. More generally, something called a reparameterization trick, which will do this for you if it's applicable. The original thing would be st+1 is a stochastic function of st and ut and theta, the parameters that you're optimizing. Reparameterized, and it's not always possible to do this, but often possible to do this. You have a new function, f deterministic, where there's a new variable there, psi stochastic, and that's a new auxiliary variable you introduce that captures all the noise. Okay? And I don't have time to go into the details of how to make that work in general, but let's look at a simple example. Let's say your next state is a Gaussian centered around some g function of st, ut, and theta with some variance sigma squared. Now what this would look like is st+1 is that g function plus sigma times psi, and all the randomness is factored out in this psi over here. And whenever you can factor out the randomness, you can make this work. In fact, if you look at it in terms of this computation graph here, effectively what it means is that you're introducing extra nodes for each psi variable that are pointing into that state s at the next time, making that function f deterministic function of psi and st and ut. Okay? So, as I said, the later things have less detail than the earlier things in the interest of time, but this actually can work quite well.
So you do need s to be continuous value and the output of f to be continuous.
Yes, for this, so there's a lot of assumptions here that are not needed for the likelihood ratio. You need your actions to be continuous valued. Otherwise, you can't take derivatives through actions. You need your states to be continuous valued. You need your reward to be differentiable. So a lot of extra assumptions need to be made. Maybe some of them can be alleviated by embedding discrete things into continuous spaces. Who knows? I'm not sure, but
the other thing is you've used the forward mode differentiation, which could be very expensive to compute if the dimension of beta and s is large. Or you could also do backprop.
Yes. Yes. So the question here is, when we look at these equations, that's how the forward mode automatic differentiation works. We can just as well do it with the backprop. Yeah. I mean, that's also the way it would be done. This was just to illustrate what derivatives are needed, and essentially also to Joshua's point that for these derivatives to exist, the s has to be continuous, actions have to be continuous, and so forth. Otherwise, you can't do this. But you wouldn't compute it this way. You would backprop to compute, which does dynamic programming over the things you compute. This idea is used in the stochastic value gradients paper by Nick Hayes and collaborators. So they essentially look at exactly this setup that I just described and backprop through it to compute their gradients. You can make variants of this because when you look at this, if you backprop through and you have the sum of rewards that you take derivatives of, you can play the exact same idea again. Sum of rewards, that's Q values. Might as well fit a Q value separately. If that Q value is differentiable with respect to state and action, I can just directly take derivatives of the Q values rather than of the future rewards. And so if you do that, you get the deterministic policy gradient or the deep deterministic policy gradient if you use a deep network to fit the Q values. And so those ideas are in those papers, but essentially the reparameterization trick applied to policy optimization, including also the ideas of introducing Q value fitting to not have a sum over all future rewards, but having fits instead. And if it's applicable, this actually learns very quickly because you use a lot more information than you use in the likelihood ratio. There's a way to generalize this. All this calculation, I don't want to get into the details, but essentially you can mix and match any kind of likelihood ratio and path derivative computation. One interesting thing is that if you have a neural network, a big neural network that's stochastic, and you have black box nodes in there, nodes where you don't have access to compute derivatives on that node, by putting a stochastic node in front of it, you can then use the likelihood ratio gradient on that stochastic node that sits in front of it, which is exactly what we did when we want to do policy gradients with no access to dynamics. That exact same idea is much more widely applicable than just to reinforcement learning. Another thing is that once you think of it this way, you don't need to rederive things in any special way. If you have recurrent policy, say, oh, what's the policy gradient for a recurrent policy? It's all the same thing. You just set up your stochastic computation graph. Some nodes you compute the likelihood ratio gradient. Other nodes you compute the path derivative, whatever seems right for that node. And you have gradients for any kind of policy architecture that you might want to use. Yes?
You might pay the price of having a high variance on the likelihood ratio estimator.
So the question is, would you pay a price of having high variance? And the answer is yes. If you use the likelihood ratio estimator, you tend to have higher variance. So typically what you would do is you would analyze your stochastic computation graph, either corresponding to your RL problem or to something else. You would see, where is my reparameterization trick applicable? Wherever you can apply it, you'd probably apply it. But then some cases it will not be applicable. Let's say you have a real dynamical system, and for some reason you're not building a model, whatever it might be, or you want a gradient on this one run on the real system, and you're not building a model, then that's the only way to do it. It could be, there are actually special cases that you can set up where the path derivative has higher variance than the likelihood ratio. All the examples I've seen are very artificial, but they involve things like if you have a function that's like sine 1 over x, which gets like very oscillatory near 0. In fact, infinite oscillations near 0. Then if you do path derivative, it'll have, the derivatives will just be going up and down, up and down, up and down. It'll be really tricky to deal with that. The likelihood ratio will have lower variance because the bounded magnitude of the actual function value. So there is some scenarios like that, but obviously sine 1 over x is not what we typically encounter in this kind of computations. But maybe there are cases where something similar happens. Essentially, likelihood ratio will do better than path derivative if there is very high variance on the derivatives. But it's less typical for that to be the case.
And the function is not of bounded variation can pay the price.
Yes. Bounded variation and high variance on derivatives will make likelihood ratio lower variance than path derivative. But I don't know any realistic scenarios. But OK, so last thing I want to do is say something about, well, we've seen a lot of methods at this point. And it can be very easy to get a headache with all these methods and think there's too many of them. So what we did is put up a table to clarify that headache. So what you see here is a set of methods that's readily applicable to continuous control tasks. On the Atari domain, there's been a lot of comparisons of methods that have discrete action spaces. This is specifically for continuous control tasks, a comparison of the different methods that exist. It suggests that in this comparison, like which methods tend to work better. It seems like the natural gradient idea, which is made even more kind of explicit and more precise in the TRPO setup, tends to do best. The deep deterministic policy gradient, which does the path derivative, does quite well too in many situations. It's a little harder to get to work, so that's why some of these entries are empty there. But I think there's some interesting questions there. If the DDPG can be made more stable, what the result would be there. If you don't want to implement them yourself, we built something called RL Lab, which makes it easy to experiment with them. It's not just, here's a snippet of code that is this algorithm. It's also, it'll output information to allow you to make graphs more easily, have multiple runs, hyperparameter settings, and so forth. So it's really like a lab software infrastructure around each of these algorithms. And it actually interfaces with the OpenAI Gym, so you can pull in a lot of environments into it very easily and see then how well does your algorithm do against other algorithms, or you just want to compare existing algorithms. So I think we should take questions at this point, and then in the afternoon I'll look at the two last topics, guided policy search and inverse RL. Thank you.